Swayam Prabha. Digital India. Educated India.
And obviously this group operation satisfies the closure property. If I add two integers, I get a third integer. So it satisfies the closure property. It satisfies associativity because the order in which I add the integers doesn't matter. It has an identity element under additions. So that identity element is 0. So anything added to 0 gives me back the same element, and that element belongs to the set. So this is the identity element. It also, there is an inverse, one more property of the inverse is that there's a unique inverse. Each element has a unique inverse. Okay, that's a very important property. So we see that this is true for integers under addition. So for example, if I take an integer, let's say 10, the inverse is minus 10 because 10 plus minus 10 is 0. That's the identity element of the group. Plus is the group operation. Okay, so for every element, I have an inverse, and the inverse is unique. Okay, there's only one thing that I can add to 10 to get back 0. Okay, so therefore the set of the group of integers under addition, or the set of integers under addition, forms a group. So really the way to say it is integers under addition forms a group. Okay. However, if I take integers under multiplication, you would see that that would not form a group. Okay, so if I take the set of all integers, z minus 10, minus 1, 0, 1, and so on, and I take the group operation to be multiplication, you would see that I could satisfy the closure property. The product of two elements would give me a third element. There would be associativity of multiplications, because multiplication, the ordering of the multiplications doesn't matter. There would be an identity, okay, because for 1 is the identity element, because 1 multiplied by anything would give me back that same entry of the that same element of z. However, there would not be an inverse element. Okay, that is, the inverse of 10 should be something that I multiply with 10 so that I get back the identity element 1, and this inverse of 10 is 0.1, okay, or 1/10, and that does not belong to the set of integers. So therefore integers under multiplication do not form a group. Okay, and the other thing that you'll see is integers under addition, they form a group, and not only do they form a group, this group also has an additional property, which is of commutativity. That is, the ordering of the addition operation doesn't matter. A plus b is the same as b plus a. So this group is also an abelian group. Okay, so but this is an additional property. This property of being abelian is an additional property which is not required for all groups. So groups are only required to satisfy the properties of closure, associativity, identity, and having an inverse element. Okay, groups which do not satisfy the commutativity are called non-abelian groups. All right, there exist at least some elements of the group such that lambda 1 dot lambda 2 is not the same as lambda 2 dot lambda 1 for these groups. Now, let's show that the matrices lambda that we have taken, which satisfy this property, the set of all such matrices which satisfy this equation okay, so these are 4 by 4 matrices under the operation of matrix multiplication these matrices form a group. Okay, and this group is called the Lorentz group. So this is a claim. We have to actually check that this set of matrices under the operation of matrix multiplication forms a group. And the way to check it is that we check that we satisfy the 4 properties listed above. So the first property is the property of closure. That is, if we take 2 matrices lambda 1 and lambda 2 that satisfy this equation, so let's take 2 such matrices, then it should be true that their matrix product, that is, if we consider lambda 3, okay, it should be true that the matrix product satisfies the same equation. That is, we want to know, is it true that lambda 3 transpose dot g dot lambda 3 g? Okay, and lambda 3 is of course a 4 by 4 matrix, so it at least belongs to the set of 4 by 4 matrices, but it should also additionally satisfy this property. So that's easy to check. Let's take the left hand side of this equation. So the left hand side is lambda 2 transpose lambda 1 transpose dot g dot lambda 2, oops, sorry, I made a mistake here. This is going to be lambda 1 transpose dot lambda 2 transpose dot g dot lambda 2 dot lambda 1. And since matrix products are associative, I can always group them together like this. And since lambda 2 satisfies this criteria, I can write this as lambda 1 transpose dot g dot lambda 1. And lambda 1 again satisfies this relationship. So this is just, okay, which is the right hand side. So this is true for any product of 2 matrices belonging to this set. I'll get back a third element belonging to the set. So the closure property is satisfied. Now, associativity is satisfied because matrix products are associative. The identity element clearly exists because I can always take this transformation for this matrix lambda, and this matrix is the identity of matrix multiplication, and it belongs to this set, okay, because lambda transpose dot g dot lambda, because lambda is the identity matrix, is just going to be g. So the identity exists. And finally, we can argue that an inverse belongs to the same set. That is, if there is an element lambda inverse, then lambda inverse must satisfy this property. Now, one thing that we should be clear about is this is the inverse with respect to the group operation, which is matrix multiplication. So in this case, the matrix lambda inverse would just be the inverse matrix of lambda. Okay. So the only thing that we need to check is the inverse matrix of lambda actually satisfies this equation. And that's easy to do, okay? So the first thing that we need is one, inverse exists and is unique. Okay, this is something that we need to check. The second thing that we need to check is that given that the inverse exists, the inverse should also satisfy this equation so that it belongs to the same set. Okay, we need to check both of these criteria. Now, the existence of the inverse is not guaranteed for all 4x4 matrices. However, all 4x4 matrices with non-zero determinant definitely have an inverse. So let's check what the determinant of any matrix is that belongs to the set. So if lambda belongs to the set G, then lambda transpose dot G, small g dot lambda is equal to G. And so if we take the determinant of this, determinant of lambda transpose dot G dot lambda G, which is the same as determinant of lambda transpose determinant of G, determinant of lambda is equal to G. Determinant of G. The determinant of G was -1. It's some non-zero number, so this is these just cancel out. And what we get is determinant of lambda transpose, determinant of lambda is 1. And determinant of lambda transpose is the same as determinant of lambda. So what we get is this. So the determinant of lambda, okay, assuming that we're making transformations with real numbers only, is either +1 or -1. Okay, you don't have any other choice. And since the determinant of any element of this set is non-zero, what that means is the inverse matrix of lambda exists and is unique. Okay. So since the determinant is non-zero, lambda inverse exists and is unique. It's just the inverse matrix of lambda. And now we just need to check the second property, that is that the inverse matrix satisfies the same property so that it belongs, the inverse matrix needs to belong to the same set of transformations, which preserve the metric. Okay. And that's easy to see also. So if lambda satisfies this relationship, we can invert both sides of this equation. And what that would give us is lambda inverse G inverse lambda transpose inverse is G inverse. So now let's multiply both sides of this equation by lambda transpose from the right. So that would give us lambda inverse G inverse lambda transpose inverse lambda t, and let's also multiply by a factor of G. So this would be G inverse lambda transpose. Okay, and now lambda transpose inverse times lambda transpose is just the identity matrix, and then G inverse times identity times G would just be again the identity matrix, and so the left hand side would just be lambda inverse, and the right hand side would be G inverse lambda transpose. All right, so what this has told us is that given the property that the matrices lambda satisfy, we have now found the matrix lambda inverse explicitly in terms of lambda transpose. Okay, and so now that we know explicitly what the matrices lambda inverse are in terms of the matrix lambda or its transpose, we can check whether the matrices lambda inverse satisfy the group property, that is, they belong to the set which defines this group. That is, do they satisfy this relationship over here? So let's check this relationship. So this relationship defines lambda inverse in terms of lambda transpose. Now we want to check that lambda inverse satisfies the property that lambda inverse transpose dot g dot lambda inverse is. Okay, so let's start with the left hand side of this equation and let's plug in what we found for the expression of lambda inverse. So we have G inverse lambda transpose G transpose dot G dot G inverse lambda transpose. All right, and we can now write this as G transpose lambda G inverse transpose dot G dot G inverse. So everything has dots between them, right? This is all matrix products. Dot lambda transpose. Oops, it's not lambda transpose. This is just lambda because lambda transpose transpose lambda. In fact, the last matrix, lambda inverse, we will just leave that as lambda inverse. We won't write it in terms of lambda transpose. So let me just erase this. And we'll just leave this in here as lambda inverse. Okay, now the thing about G, if you remember, is G is this matrix with zeros everywhere else. And so G inverse, since this is a diagonal matrix, is just going to be the same. Okay, you can easily check this. And therefore G inverse transpose is also the same. Okay, that's just equal to G. So G is the same as G inverse, which is the same as G transpose, which is the same as G inverse transpose. All right, so what that does is it tells us that G inverse transpose can be just written as G inverse. So the left-hand side of our equation is just G transpose dot lambda inverse, where I just combine these two into an identity matrix. And lambda dot lambda inverse is again an identity matrix. And G transpose is just G, so this is just G, which is the right-hand side of our equation. Okay, so we have checked that lambda inverse satisfies this equation. So lambda inverse belongs to G and is unique because matrix inverses are unique if they exist. And we've shown that they exist because the determinant of lambda is either +1 or -1. So now we know that the matrices lambda form a group, but now we'd like to know, what do these matrices explicitly look like? So what do the matrices explicitly look like? That is, can I write down the exact matrix? So we can write down a few examples of such matrices which satisfy the property that lambda transpose dot G dot lambda is G. So let's write down a few examples. So one of them we've already written down is the matrix of this form: gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. And this corresponds to taking us from a frame S to a frame S prime, which is moving at a relative speed beta along the x-axis. Okay, so to be clear, we can write beta as v by c, and if we want to clearly identify that this is a transformation along the x-axis, we can put a subscript x here and a subscript x here, and we can write it like this. Okay, where in this case gamma is 1 over the square root of 1 minus beta x squared. Okay, and so this transformation takes us from this frame S to this frame S prime. So this transformation is also sometimes denoted as Bx, which is short for a boost along the x-axis. So now, given the form of this matrix, you could also guess that we could also have matrices of this form. So let's say gamma 0 minus gamma beta 0 0 minus gamma beta 1 0 0 0 gamma 0 0 0 0 1, and this would be by, or a boost along the y-axis. In this case, obviously the parameter beta is different. Okay, this corresponds to a boost along the y-axis, so this would be taking us to some other frame where the boost, let's put a beta y. Okay, and this gamma, to be clear, okay, really is let's say gamma y. Okay, and this gamma was gamma x. So beta y was is Vy by c, where S double prime is moving with respect to S at a speed Vy, and gamma y is 1 over the square root of 1 minus beta y squared. Okay, so this is an obvious additional transformation, which is you can go to a frame which is moving with a speed v along some other direction, like the y-axis. Okay, and similarly you can construct bz, okay, which would have non-zero entries only here and here, and everything else would be zeros. Okay, so this would be a boost along the z-axis. So these are obvious extensions of the transformation that we already wrote down. But in addition to these, you would also have matrices of this form. Okay, so let's let me write this down. So 1 0 0 0 0 cosine theta minus sine theta 0 0 sine theta cosine theta 0 0 0 0 1. And this is this corresponds to going from an observer or a frame S with axes, let's say x, y, and z, to an observer in a frame S prime whose axes are rotated in the xy plane. So this is x prime, y prime, and z is still in the same direction. Okay, and it's a rotation by an angle theta. Okay, so the y-axis and the x-axis have both been rotated by an angle theta. It's just a rotation in the xy plane, or it's a rotation about the z-axis. So this transformation, okay, is a rotation in the xy plane by an angle theta. Okay, so in this case, there's a continuous set of rotations where theta belongs to 0 to 2 pi. Okay, and if you want to be explicit, you can say this is theta in the xy plane. So of course, since in 3 dimensions, if you want to define a plane of rotation, that is the xy plane, you can also talk about the axis of rotation, because there's only one direction in space which is orthogonal to the xy direction. So sometimes this is denoted as a rotation about the z-axis by an angle theta, right? And so one important thing is that the transformations beta x, bx, by, and bz, they depend on a single parameter, in this case beta, where beta lies between -1 to +1. So there's an independent transformation parameter for a boost about the x direction. There's a separate independent parameter for a boost in the y direction, and a separate parameter for a boost in the z direction. Okay, strictly speaking, this is an inequality, not an equality, because you cannot have a well-defined transformation to a frame which is moving at the speed of light. Okay, so you need to be traveling at a speed less than the speed of light. And these transformations are of rotations must be between 0 to 2 pi, because 2 pi is the same thing as a rotation by 0. And similarly, you can write down transformations. You can write down transformations for rotations in the YZ plane by an angle theta, and a rotation in the XZ plane by an angle theta. Okay,